Hi guys, welcome back. So I hope you tried to investigate what we've been talking about before we went to the ad break, right? We looked at what happens when I move a point around, right? That moving of a point is all about trying to see what the relationship is between the angle that is formed in between the two lines, the radius and the chord, and also how the radius cuts that particular chord. Now we're going to try and draw some conclusions based on that investigation. And then one thing that makes us one of a kind as mathematicians is that we always have a proof for everything that we're talking about. After all, you know that mathematics teachers always say they've got problems, but our problems always have solutions and they always have proofs. So we're going to try also and look at a proof of what exactly is it that we're going to say in terms of a conclusion, and what happens when now we twist it around. Is it still true or not? So that's what we're going to be looking at. But for now, let's just look at our mind map and try and see what we've looked at so far. Right? So far we looked at the concept of a radius, which we said was a line from the center of the circle to the circumference of the circle, and then we said twice the radius then gives us the diameter of the circle. We also had the line called a chord, and a chord will be a line from one point on the circumference to the other point on the circumference. It doesn't necessarily need to pass through the center, right? When it passes through the center, we no longer call it a chord. It has a special name, which we said is a diameter. So please remember that. Now, we have what we call a conjuncture. Now, I said to you, what makes us special as mathematicians is that we have proofs. A conjuncture will be like a baseless claim, right, that has no proof whatsoever. So we're going to try and make a conjuncture. The conjuncture will be based on this investigation. What did we see in terms of the observation, right? So as mathematicians, what we do is we observe things and we get fascinated by those observations, and then we try and use some math to prove exactly whether what we are seeing with our eye is always true or not. So that's what a conjuncture is all about. A conjuncture will be a claim that has no proof that supports it or anything like that, is really based on observation and what you saw when you were trying to maybe do an investigation. And then only after when you analyze, you can then have a proof. Then we can call it a theorem, because then now it has a conjuncture, which is what we saw with our eye when we were trying to do that. But now it has a proof. Then it qualifies to be a theorem. But if it's only an observation, really, remember they always say looks are deceiving. So make sure that you understand this. Now, the summary of the observations that we saw with that particular thing that we're doing is that when the angle between the radius gets close, right, the radius and the chord gets close to 90 degrees, we saw that the segments of the chord are equal in length, right? So if I have that center there, the radius there, and I have my chord there, if this angle becomes 90 degrees, the conjuncture of the observation is that those two line segments there become equal to one another. So that's what we are at the moment. We're going to try and prove this if it does really exist or not. We also have what we call a converse. A converse is to say if this that I have is true, if it is perpendicular to one another, it means that this line and that line are equal. The converse will be if this line and that line are equal, it means the two lines are perpendicular to one another, right? So if this line segment here, let me just maybe draw it this side so you can see exactly what I'm talking about. The converse of the same thing we are talking about here is if this line is passing through the midpoint, right? Meaning it is cutting this line, the chord into two equal parts. It would therefore mean that it is perpendicular to it. That's what the converse is all about. So when the radius intersects with the midpoint of the chord, that's what I just said, then the angle between the radius and the chord is 90 degrees. That's what the converse says. It's another conjuncture, but you must remember that because it's an observation that we have. After all, with an observation, remember guys, if I say it takes 20 kilometers to get to the mall, I can then say to get to the mall, it takes 20 kilometers. Right? So I can tell you how long it takes to get there. Also, I can say if I want to go to the mall, it means that I must then walk or I must drive 20 kilometers. So that's what the theorem and the converse is all about. If this is true, it means it can also be true that because I want to get to that point, I will have to travel this distance. So that's what we're going to be talking about with this particular thing. Now, the key words here is we have what you call a perpendicular. Remember, we've been looking at this in the previous grades. Perpendicular, we normally use this sign, right? It means that they make 90 degrees with one another. So if I say these two lines are perpendicular, it means there is a 90-degree relationship between the two lines. That's what perpendicular is about. Bisector would then mean, bi means two, right? So bisector, it means the line is cut into two equal parts, right? Into two halves. So if this line is bisected, my line AB is bisected by M. It means that AM is equals to MB. That's what bisector means. Then midpoint, same thing as what I just spoke about. So bisector is what cuts it, and then that point where it is cut into two equal parts is called the midpoint. Now we have what we call inductive reasoning, guys. Remember, inductive reasoning is based on trying to see whether this is always true or not. We are trying to induce and see exactly whether this will always be the case. The big question for you: are our conjunctures always true or not? We don't know. Only based on proof can we then make the claim that they will always be true or not. The condition must be this or not. So that's what we need to talk about. What if we change the size of the circle? You see, that's what I'm talking about, to say the condition, if we then change the size of the circle, does that make the conjuncture to still be true or not? Does then change it or become something else? That's what we need to be thinking about in trying to do Euclidean geometry. We also have deductive reasoning. Based on something that we already know, we go back and try and talk about what is the truth of the matter. Now, our theorem is to say the line drawn from the center of a circle perpendicular, condition, perpendicular to a chord. It bisects the chord. And then if you were to be asked a question and you're trying to use this theorem, your reason is normally line from center perpendicular to chord, right? So the condition is if it is drawn perpendicular to this chord here, then the chord is bisected, right? It is cut into two equal parts. So what do we know? We are given the circle with center O and line OP, as you can see on the board. Line OP lies on the radius, though I did not complete it until the last point, or the point on the circumference. And then this is perpendicular to chord AB, right? Now, I don't know, guys. See, one thing I can tell you now is, if I did not tell you, you do not claim it. Euclidean geometry is that. You know this thing that they normally say, monkey see, monkey do. You know when you go to the zoo and you're looking at monkeys, what you do is they always gonna try and do it. We don't do that here. Because it looks like it, it does not make it it. I need to tell you that this is the case for you to then claim. So I need to tell you that I have a center, and also the center is perpendicular. Then you can claim that, yes, the line is bisected. Or I need to tell you that there is a center, and the line from it passes through the midpoint. Then the conclusion will then be it is perpendicular. So I need to tell you, you don't make claims without being told a key word. So, and also one thing, I always see people doing Euclidean geometry and they think, I thought this was not important. There is no way I will waste my ink and write things on the paper that I give you as a question paper maybe, and there is nothing important there. Everything that is there is important. You just need to know and think about it and see where to apply it. So, monkey see, monkey do does not apply. Because it looks like it does not make it. Please note that. Now, what we are required to prove, also by the way, they normally use RTP. You will be seeing a lot of it in maybe your textbooks or later on when we try to do this. I'm required to prove that this is equals to that because of that 90 degrees there. So my proof will be, firstly, there's what we call a construction. You need to draw OA. You can see there's OA there, and also draw OB there. If you do that, you will then say in triangle AOP and BOP. So the beauty of math is it's a language, right? You're talking to me and telling me where must I focus, right? My focus will be in those two triangles. And in those two triangles, we can see that angle APO is equals to 90 degrees. That's what we were given. But because of it's 90 degrees, angles on a straight line make 180. It means also BPO is also 90 degrees because that's what we know in terms of angles on a straight line. Then AO is equals to BO. That's the radius of the circle, right? But because it's plural, we normally say radii. Now, I did say that any line drawn from the center to the circumference of the circle will always be equal. So those two lines are equal. And then also, OP is equals to OP. Clearly, it is one side that is common in both the two triangles. As a conclusion, I will then say that triangle AOP is congruent. Remember, this is congruency. Is congruent to triangle BOP. And my reason will be, I proved a right angle triangle, a right angle I proved the hypotenuse side, which is the longest side, and one more common side between the two. Now, what they wanted me to prove was AP is equals to PB. This, I normally use the reason CP, CT, C, right? Now, I will explain. This means congruent parts of congruent triangles are congruent, right? So if I've proven that the two triangles are congruent, it means all the parts of those two triangles will all be congruent as well. Remember, congruent means equal, right? So if I prove that these two triangles are congruent, everything in those two triangles will then be congruent. That's what that CP is. But at times they just use from congruency. You don't need to use those letters there. And then what I then know is, remember with my converse of this is to say, I said if it passes through the midpoint, then it is perpendicular to it, right? But we will look at that at a later stage. But now the big idea here is we were trying to see that if this line, that is my radius, is perpendicular to this line, which is my chord, then the chord will then be bisected, meaning cut into two equal parts. And this is my proof. Because it's a formal proof, there's three things that you always need to do. It's what you are given, what you are required to prove, and then your construction, right? And then lastly, which is the fourth thing, that what you need to try and do, then your proof, right? So you look at what is it that you are given, what do they want you to do, you construct, because it's a formal proof, and then you start with your proof. And then from there, you will then be done with this. So remember, with a formal proof, there's always a need for you to tell me, what did I give you? Because that's what determines what you can do, excuse me, with that. Also, what do I want you to do? The required to prove. 3, do you have sufficient information or not? If you do not, then construct, right? You do say construction and tell me what you did. Lastly, then prove it. Let you try and digest that for now. I'll be back with some more after the ad break. Stay tuned.